So today we are receiving Alix Deleporte from the Laboratoire de Mathématiques d'Orsay, who will talk to us about classical and quantum normal forms for circular wells. If you want to ask questions during the talk, you can either unmute yourself and ask the question or ask it in the chat where I will relay it to Alix. And otherwise, the floor is yours.
Thank you, Jean. I would first like to thank the organizers Jean Lagacé and Alexandre Giroir for giving me the opportunity to talk here and for the nice organization. The thing I will be talking to you about today is a joint work with Stan Vignoc from Rennes. And it's something I did when I was a postdoc, first at MSRI and then at the University of Zurich, which is where you can see three affiliations on my first slide. But right now I'm at Université Paris-Saclay. Before describing the problem, I will first present to you with some kind of toy model where you can see what's happening. The toy model is a quantum magnetic field on a circle. Generally speaking, the quantum magnetic problem, what does it mean? It means that you're looking at the evolution with respect to t of some function psi of x, which is an L2 function, and which satisfies this linear differential equation, which you might already know about. So the differential of psi with respect to t is some kind of Laplacian Laplace operator as applied to psi, and this Laplace operator is shifted in momentum by some function a. In a, if you know a bit about classical electrodynamics, is the potential vector. So the curl of a is a magnetic field b. And we're looking at this problem in 1D, and more specifically, psi will be a function of t in R and of x, which belongs to S1. And it might seem puzzling because usually in one dimension there is no magnetic field. The important thing is the curl of A, the differential of A as a one form, which is a two form, and when one dimension, so there are no two forms, B is 0, there should be no magnetic effects at all in this problem. But here, if the spatial domain is a circle, we will see non-trivial effects. And so let's forget about all those magnetic fields and try to reduce the problem. So the way to reduce the problem is to consider the spatial average of your potential vector A over S1. And then A minus A bar is a function on S1 with 0 mean, so that there are primitives on S1. And if you conjugate your operator, well, the square root of your operator with an exponential of this primitive, then you've simply replaced the function a of x with the mean bar a. And thus, if you just conjugate, you can just conjugate the equation into something which has a similar form, but now the differential operator in x, which you apply, does not depend on the position. So the quantum evolution is diagonal in the Fourier modes with respect to the variable x, and you get some eigenfrequencies which are the squares of 2 pi h bar k plus a bar, where k is any integer. And so this is very well, but now the behavior of this spectrum depends on a bar, and in particular it depends on a bar modulo 2 pi h bar. And for instance, if you want to look at the ground state energy, the lowest eigenvalue of this operator you're going to have some oscillations with respect to A bar or with respect to 1 over H. As H goes to 0, or equivalently as the magnetic intensity increases, you have some oscillations. The results of our work is that there is a very general class of classical and quantum systems, which we call circular wells, for problems with problems in 1 dimension, and for which one can generalize the conjugation trick above. And for those systems, in some cases, you can see there's oscillations in the spectrum as H bar goes to 0. And as a kind of illustration, I will present you with the little Parkes effect. So quantum problems in 1D in general are very exciting because there are model operators for general magnetic fields in several dimensions. And in particular, this oscillation behavior is related to the little Parkes effects. The little Parkes effect is as follows. You take a thin and hollow cylinder, such as this one, but imagine it's made out of a supraconducting material. It's made out of a supraconducting material, and you apply to it a magnetic field which is parallel to the axis of the cylinder. And now you measure the resistivity between 2 points, from one side and the other side of the cylinder. And you plot this resistivity as a function of the magnetic field which you applied. And you find these oscillations. This is an actual picture from an actual physics paper done by actual physicists. You have oscillations, and it's really the average of the magnetic field over the circle who counts. This little Parkes effect has been directly analyzed, and in the recent years there have been some progresses on the question, but it's still one of the nice examples of what we can do with our general quantum 1D problems. Now I will describe to you the classical problem, and since I have no idea of the audience, I'll start very slowly. So I'll start with the Hamiltonian formalism in classical mechanics. We're in 1D, so let's start with fairly general equation of motions for a 1D particle. You have a massive 1D particle which is subject to a force deriving from a potential. And in this case, the Newton's law of motion tells you that the acceleration times the mass, but here the mass is 1, is given by the force, which is minus the gradient of the potential. Here we're in 1D, so our system is just the derivative of the position is the velocity, and the derivative of the velocity is minus the derivative of the potential with respect to the x variable. And in terms of the one interesting function in this setting, which is the total energy, kinetic energy plus potential energy, you can write this as time derivative with respect to x is velocity derivative of the energy, and the time derivative of the velocity is minus x derivative of the energy. So the recipe to obtain the equation of motion and the evolution of the system is as follows. You consider first the gradient of the energy, which is a nice vector field on R2 on S1 times R, if x is a variable in S1. You perform a quarter turn on this symplectic, on this vector field, and you obtain what I will call the symplectic gradients. And then you follow this vector field, and this is your time evolution. I've talked to you about symplectic, so let's talk a bit more about it. The gradient, as you might already know, is not something that behaves very well when you change variables. And in general, the notion of gradient is associated to the data of a metric. And there is a magic equation which tells you that if you take the metric element between the gradient and any vector, which means that's just a scalar product between the usual gradient and a vector field, then what you get is just the derivative of the function you started with in this direction. And in the same way, associated with your symplectic gradient, which is just the usual gradient on which you perform a quarter turn, is associated symplectic form W, which is omega, which is just a gadget which eats two vectors. And if it eats the symplectic gradient in any vector, it spits out the derivative of the function you started with respect to this vector. If you already know a bit about symplectic geometry, it's a very good idea to think of the symplectic world as the metric world on which you perform the quarter term. Here we're in dimension 1 plus 1, 1 plus 1 because there's one dimension for x and one dimension for v. And here the symplectic form is simply the volume form. So the omega is simply the determinant of the matrix with psi e and x. And another gadget which will be useful and which is associated with so the symplectic form is the Poisson Brackets. Given two functions, say two smooth functions on a manifold with a symplectic form, you can compute a third function, which is the Poisson Brackets, which I simply define as the symplectic form which eats the symplectic gradient of the first function and then of the second function. If you're in the coordinates, which I wrote above, this is just the cross product of the derivatives of f and g with respect to x and v. This Poisson bracket is interesting because it gives the commutator of the dynamics. To the function f is associated, if I think of f as an energy, some classical dynamics. And to the function g is associated another classical dynamics. And if I let them evolve in a very short time, in general, the evolutions will not commute. And the commutator of the evolution is given by the Lie bracket of the vector fields. And the Lie bracket of the vector fields is up to a minus sign, the symplectic gradient of this Poisson bracket. Now, I'm telling you all of this because we're trying to start from a very general equation of motion, very general form of the energy, and try to simplify it, just as we did in the toy model. And if you find a transformation, a change of coordinates, which preserves the symplectic form, which preserves the volume, then it will preserve the equation of motion, because the equations of motion are just given in terms of the symplectic form. And a nice example of transformations which preserve the symplectic form are classical dynamics. So if you take some dynamics associated with the function f, which you don't know about, but what you do know about is the evolution associated with another energy g, then you can just conjugate the evolution of f with the evolution of g, and it's done in a very transparent way. That is, what you're going to see is just the evolution of the pullback of f by this transformation. And you can compute this pullback or this push forward by the following transport equation. And I'm sorry because S became T, but you can still make sense of this transport equation. So now we are armed to deal and to simplify the classical problem. So what kind of general theorems do we have to simplify evolution of Hamiltonian dynamics in dimension 1 plus 1? And in the rest of this talk, M will be either R2 or S1 times R. And the most simple thing you can try to do is to simplify, to find nice coordinates near a non-degenerate level set of your energy, which is a circle. And the angle action theorem, or the simplest angle action theorem, for which I quote Deustermatt. Deustermatt did not come up with this theorem. It was known long before him, but just this is a nice proof. We can see everything. So if you take any function P naught and any compact connected component of a level set where the function is non-degenerate, then you can find a symplectic change of variables which maps this to a neighborhood of the zero section in S1 times R, such that when you apply this change of coordinates, now your function is just a function of the action I. And it's very interesting to have only a function of the action I, because now the evolution is fairly simple. I does not move, and theta moves by a constant amount, G prime of I. And here, in addition, G is a locally a symplectic diffeomorphism, so G prime is non-zero everywhere. You can somehow prove this theorem just by drawing pictures. So here is your curve gamma, which is a, say, connected component of your level set P naught equals something, and you want to map it to a neighborhood of the zero section on your cylinder. And you want to do this in a way which preserves the volume form. So if I take any connected component of a level set which is just above or just below, it's gonna be a circle which is near the original gamma. And there's only one way, well, there are two ways, but let's choose one. There's only one way to map it into a circle I equals constant in a way which preserves the volume. So the volume on the left is equal to the volume on the right, and that gives you the function G. And once you have the function G, you can complete the construction of the coordinates by just taking any curve which is transverse to gamma and saying, well, now this is theta equals 0, and now from theta equals 0 we can reach any point by just following the dynamics. And since on the right side I know exactly what the dynamics are going to be because they're given by G, then I know exactly what theta should be. And once you have the variables theta and I, you can check that this preserves the volume form. And that's all there is to this angle action theorem in 1D or in 2Ds. More generally, you can find action angle coordinates, say, near the second most simple thing after a non-degenerate circle, which is a most critical point. If you have a local maximum or local minimum or a saddle point, you can have you have action angle coordinates near near this point. And I quoted Arnold because in the book Methods for Classical Mechanics by Arnold, somewhere towards the appendices, there are nice proofs for all of this. But we're interested in a setting which is not Morse. Our toy model was the following: function P naught to theta and psi, you associate theta minus a of psi squared. And this is not Morse. This reaches its minimum on a closed circle. We're generally going to consider functions P naught from M to R, which reach their minimum on a closed curve in in a non-degenerate, in a transverse non-degenerate way. And we're gonna see what it means on the next slide. So what it means to reach the minimum in a non-degenerate way is that the Hessian at these points, at these minimal points, has maximal rank. It cannot have rank 2 because it reaches its minimum on a circle, but it can have rank 1. And let's assume it has rank 1 everywhere, as it does for the example above. And so we call this hypothesis the circular wares. This is just a Morse-spot condition. And in this setting, then we can find a symplectic change of variable sigma and a function g, which are just as in the usual angle action theorem above, such that in those new coordinates, the function p naught is just this function of I squared. And the way it works is if you assume that you have a Morse-spot function on a two-dimensional manifold reaching its minimum in a non-degenerate way in a closed curve, then this function has a smooth square root. So there exists f such that p naught is f squared. And then you can just apply the angle action theorem to f. And then you find your function g, and well, p naught is f squared, so it's in those variables, it's g squared. And the Morse-spot condition exactly means that your function f is non-degenerate on the curve gamma. Its derivative is non-zero. In the example that we treated, there's a simple way to find this. There's a simple symplectic change of variables which reduces this to a function of one variable. You can just shift psi by a of theta, and this gives the function g, which is the identity. So this is what I was talking about when I say that usually there are no magnetic effects in 1D. That's because if you try to reduce the classical problem, you will find something which doesn't depend at all on the magnetic potential. So this A is artificial at this stage, and you can simplify it. Okay, now let's try to put some semi-classical analysis in the picture. And for this, I have to tell you or remind you of what the semi-classical correspondence is. I described to you just before classical mechanics, and before that, I described to you quantum mechanics, and now we're trying to put these two worlds together, or at least in correspondence. On one side, your data is something moving on a symplectic manifold M. And on the other side, it's an L2 function over R over S1, so it's an element of some Hilbert space. And the energy on one side, we say there's any kind of function from M to R, and on the other side, it's a self-adjoint operator. And given this function, or given the self-adjoint operator, you have you can have the, well, given these, the equation of motion are given on one side by the Hamiltonian flow, and on the other side by the unitary flow of your operator. And the commutator between the flows on the left is given by the Poisson brackets, and on the right, if you try to commute two small quantum evolutions, you're going to retrieve the commutator, the Lie brackets of the operators. So what does it mean to put quantum mechanics in the picture? It means associating in some way to the function P a family of operators which depend on a parameter H bar, such that the the Lie bracket corresponds to the Poisson bracket at first order. You can never reach this without the bigger of H2 error, but you can at least reach this at order 1, and that's what we're going to do. One example of quantization, there are many others, and that's the one we're going to stick with in this talk, is pseudo-differential operators. So M is a cotangent space. So here it's the position space times the momentum / velocity space. And quantization means that each time you have some psi, you replace it with differentiation with respect to x. And that's what we did previously. The magnetic energy psi minus a of theta squared corresponded to the magnetic Laplacian minus a h bar dx plus a of theta squared. And in this semi-classical world, what you do is you start with some symbol P0, and you manipulate it. Say you conjugate it with some other quantum evolution, or you do things, and you're going to have to deal with perturbations with some kind of formal series, where your first term is going to be the classical energy P0, and then you're going to have a series of other terms which you don't control very well. You just know that they are here, and you want to reduce them, but you have to deal with them. The very specific problem we have here, and it's a problem that you don't have if you're dealing with a simple trajectory or with a Morse critical point, is that the geometric hypothesis having a circular well is not stable under perturbations. If P1 and P2, etc., are say Morse functions, fairly general functions, then this perturbed function will not reach its minimum on a circle. So this means that our angle action coordinates, which we figured out a few slides before, cannot be stable by perturbations, because if you perturb the problem, you're going to have something which has, say, Morse critical points, and you can apply the Morse critical points angle action theorems, but they have nothing to do with what we found out before. So we have to find a way to go around the fact that those angle action coordinates are not stable by perturbation. And we'll try to reduce this, these perturbations by staying close to the initial coordinates, but trying to get rid of as many terms as we can. So let's start with the first term. Okay, the zero term P0, we already simplified it. So you apply your first angle action theorem, and you find that you have your function g squared plus h times something P1. And here g of 0 is 0, and g prime is now equal to 0. First, we isolate the value at I equals 0 in P1. So P1 is equal to P1 at I equals 0 plus something else. And the something else, since it vanishes at I equals 0, is a multiple, is a smooth function times g of I, g prime of I, because g of I is 0, g prime of I is non-zero. Then you have this new arbitrary function R, in which we further isolate the theta average. So you have three terms now, P1 of theta 0, which depends only on theta, plus one terms which depends only on I, plus one terms which is g of I times g prime of I times something whose mean over S1 is 0. And now we are going to push this by the flow, Hamiltonian flow at times h of the primitive with respect to theta of a primitive of r minus r bar. And then if you do the computations, this factorization g of I, g prime of I was done just in the right way, so that what you find out is after once you apply this evolution, that you have something which depends only on I and which is a small perturbation of the original thing, g of I plus h bar something squared, plus h bar something which depends only on theta, plus a remainder. And then by induction, you can eliminate, you can curl all of the powers of h bar. And you reach the following conclusion, which is that if your main term P naught has a circular well, then there is a formal symplectic change of variable. So symplectic change of variable sigma naught plus h times something, etc., such that in a vicinity of the minimum, you have a non-degenerate function of I squared plus h times some function of theta plus O of h infinity. And given this, we can now try to analyze the quantum problem and find the spectrum of this quantum operator. But what I want to say is that at this point, there is still no oscillation phenomenon. The A bar that we had before is still not apparent here. Here is a picture of the phenomenon that I was talking to you about just before.
Alex?
Yes?
Sorry, could I ask a question briefly about the previous statement?
Yeah.
Should we interpret the sort of the dot 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 on the right-hand side of this quantity squared as saying that if you were to sort of truncate at some finite level like r to the capital N, that the square of that finite sum would plus the other finite sum of these would differ at most by h to the n plus 1 from
Yes,
P.
that's
okay.
it. That's it.
I just wanted to make sure I was understanding this.
Yeah. That's what I mean. Yes, sure. Here is the picture that the picture of the phenomenon that I talked to you about. That if you perturb your original function P naught, you're going to see typically a Morse function. And here this is a heat plot of some nice function, which has a nice circular well, plus some small perturbation. And you can see that there are some parts where it's smaller, the red parts here, and also there is a local minimum, and then there are local maxima here, and there. So this circular minimum is broken. And all of this is happening at scale h. And if the function v naught is Morse and you have this kind of picture, then you have what we call mini wells at the points where v naught is the smallest, and mini saddles at the points where v is the largest. And the terms mini wells and mini saddles is not new. It originally appeared in an article by Helfer and Justrin where they're trying to they were doing things for a related problem where you consider a Schrödinger operator, no magnetic form, the Laplace operator minus h bar squared Laplace operator plus v, and the potential v reaches its minimum in a Morse-bot way. And here in this setting, you have a similar phenomenon where at scale h bar you have things happening. You have some sub-principal term, which is making all points where v is minimal not equivalent to each other. And here, not all points where P naught is minimal are equivalent to each other. So it's the same thing. Okay, so now let's try to fully quantize this thing. I've talked to you about, quantizing functions, but not about quantizing symplectic change of variables. So what happens if you try to find the quantum version of a symplectic change of variables? If your symplectic change of variables is given by a time evolution of some energy, well, you can just quantize it by considering the quantum evolution, and the quantum evolution is going to mimic the classical evolution. That's the Egerloff theorem. But unfortunately, not all symplectomorphisms come from Hamiltonian flows. And the simplest example of a symplectomorphism which does not come from a Hamiltonian flow and which is forbidden in the quantum world is the vertical shift on the cylinder. Of course, this change of variables, which I wrote just here, is a symplectic change of variables. But there is no quantum equivalent for this guy. In the quantum world, you cannot shift up and down your cylinder. And more generally, the one form I d theta, whose differential is the symplectic form, is preserved by any Hamilton flows, and in fact is going to be preserved by any quantum any symplectic change of variables which you can quantize. And this leads to to a Hamiltonian invariant and a quantum invariant for curves, which went once on S1 times R. If you have a curve which makes one turn around the base circle, then you can define, well, it's very, it looks like things we were looking at previously. You just take the area here and you divide it by 2 pi. And this is what's called the Bohr-Sommerfeld invariant. And this invariant is going to be preserved by any quantum transformation, any Hamiltonian transformation which you will do to your system. Well, there is another simpler invariant on curves, which is if your curve is contractible, if you have any curve on R2 or contractible curve on S1 times R, then there is a simple Hamiltonian invariant, which is a symplectic invariant, which is the area enclosed by this curve. Since symplectic transformations preserve the enclosed area, well, they preserve the area, and so this is another invariant for curves in another subset of the, for curves which are contractible, we have one invariant, and for curves which wind once, we have one invariant. And the question is, how do they relate to one to another? And in fact, the symplectic polar coordinates, the usual polar coordinates do not preserve the volume form, but you can make a change of variables on the radius variable so that it becomes, so that it preserves the volume. So this symplectic change of variables from R2 to S1 times R, this one can be quantized. And the symplectic transformation precisely maps the enclosed area of a curve winding around 0 to the I naught of its image, which we defined on the previous slide. So the link between the I naught for contractible curves and the I naught for curves winding once is this polar change of coordinates. You can construct this quantization in a very simple way. You just have to identify the Hilbert basis for the quantum harmonic oscillator, the semi-classical quantum harmonic oscillator, with the usual Fourier basis of S1. If you do this, well, this is a nice quantum transformation. So you can prove that this is a Fourier integral operator and all that. And the associated symplectic transform is precisely the one which is in the proposition. So here is a picture for the Balsamorphic invariant in both cases. And this leads to the complete statement, which is that given any pseudo-differential operator for which the principal symbol has a circular well, and given the Balsamorphic invariant I0 of this well, which makes sense where the gamma is a curve which wins once on your cylinder or which is contractible, then there exists a unitary map on the well-defined on the low energy spectrum of your operator, which conjugates your quantum operator to something which is close to what we had before, something which depends only on psi, on d theta squared plus h bar times something which depends only on theta, but where you shift it by I0. And you have to shift by I0 in order to preserve the Balsamorphic invariant. And here, GH bar and VH bar have expansions and are formal symbols. And if we're dealing with pseudo-differential operators, then V0, the main potential term in your reduced operator, is exactly the original subprincipal symbol you started with, restricted on the curve. So you don't have to make very hard subprincipal computations to obtain V0. It's just the original subprincipal symbol if you're dealing with pseudo-differential operators. And here, well, this is the generalization of the trick in the time model that I talked to you about. This UH bar and UH bar star is the generalization of conjugating with exponential of the primitive of A minus A bar. And well, now that we have this, we can try to analyze the low energy spectrum, for instance. In the low energy spectrum, two things can happen. Well, if V0, say, is not identically zero and it's Morse, then in fact you don't see these oscillations. The low energy spectrum of your operator is going to be driven by the mini-wells that are here. That is to say, your low energy quantum states are going to be localized, say, in the red region or maybe in the green region, but they're not going to be located on the whole circle. On the contrary, if V0 is identically zero, well, then you have to get to next order to know the perturbations. But in fact, it stops. If V0 is identically zero and you have to get to the next order, then the oscillations win. And then you have some at the limit, you have some periodic properties of the eigenfunction, of the eigenvalue with respect to h bar as a function of 1 over h bar. And here is a nice plot for a quantum system on which V0 is equal to 0. And again, it's not hard to find out a pseudo-differential operator for which V0 is equal to 0, because you just have to find one when the subprincipal term is equal to 0. And if you compute numerically the spectrum, you can see that in this example that the two first eigenvalues, for instance, are going to oscillate in a periodic way. And not only the periodic, but the frequency with respect to 1 over h is exactly the Balsamorphic invariant I0. Here you have every 2, so 1 over h bar needs to increase by 2, and that's because our principal symbol had a circular well on the unit circle, which for which the area is pi. So the in this case, the Boltzmann-Mulford invariant is 1/2 because it's pi divided by 2 pi, and it's exactly this. So not only there are oscillations, but you can recover I naught from these oscillations. You can hear it in the low energy spectrum. I'm done now, and I will now present you with two kind of general perspectives. The first perspective is what happens in higher dimensions. Of course, in higher dimensions, not all classical systems are integrable. So what happens? The Boltzmann-Mulford invariant generalizes to Lagrangian submanifold in general. Can we hear this invariant as some kind of periodicity in the low energy spectrum? And for this to happen, does the system needs to be integrable, or can we also hear this on non-integrable systems? The other perspective is, what about tunneling? What if in the picture here, what if the picture was actually symmetric? V0 is not 0, so things are in the low energy spectrum are driven by the mini-wells, but you have 2 symmetric mini-wells, or say 3 symmetric mini-wells. In what way, what kind of tunnel effect do we have? And there are nice numerics and also, I think now, proofs in one case that you do have tunneling at some fractional power of h bar. And not only this, but at this amplitude, you have oscillations, and the eigenvalues, the 2, the 3, the n eigenvalues which tunnel and which are very close to each other, actually intertwine in a nice way with some periodicity given by the Boltzmann-Mulford invariant. This is what we hope to prove. So I'm done. Thanks for your attention.
Thank you very much, Alix. I think everyone is joining me in clapping.